Hi, everybody. Welcome to Beyond Lambda, introducing Delta architecture. There we go. My name is Denny Lee. I'm a developer advocate at Databricks. I'm basically a hands-on distributed system and data science engineer. In my past, I used to be part of at Microsoft as part of the SQL Server team. I also helped build what is currently known as Azure HD Insight, currently known in the project called Project Isotope. I've been working with Apache Spark since 0.5 and been loving it and having a great ball talking about some of the cool projects and problems that we are solving here at Databricks. And so the agenda is sort of as follows today. What are the complexities to build a simple data pipeline, and why do these complexities even exist? And then when we talk about these complexities, we also talk about how Delta Lake, why Delta Lake and how it works, and then talk about the Delta architecture. This is a pattern that we often see with Databricks customers, but then in terms of building continuous pipelines with Delta Lake and how we want to apply that to everybody. So with the open source Delta Lake project and the key characteristics and benefits of this Delta architecture. And so if you go backwards a little bit and talk about what is a data engineer's dream, right? The dream of that person is to go ahead and, excuse me. The dream of that person is to go ahead and be able to process data continuously and incrementally as new data arrives in a cost-efficient way without actually having to choose between batch and streaming. Right, the whole premise of structured streaming and Spark, when we built structured streaming, was the context or the idea that you didn't want to actually differentiate between how you dealt with batch data versus how you dealt with streaming data, right? Basically, this concept of continuous applications. You want to basically say, I don't have to choose between batch or streaming. I just want to be able to go and handle both at the same time. It's just a matter of latency, right? But in reality, this is actually how it looks. And so you can replace Kafka with, if you wanted, with Kinesis or with Event Hubs or Cosmos DB. Doesn't really matter. The context is that you have a bunch of events coming in, right? And traditionally, you have a batch type system. So you stream that data from Kafka into structured streaming, and it gets written to a table. This table basically is then loaded. And then we have another streaming job that reads that table to basically go ahead and do our AI and reporting. As time progresses, the job becomes the job will exponentially become slower because due to the buildup of very many small files. Okay, that's problem number one. And so how you typically solve that problem is by going ahead and switching that table to batch, and then basically with that table, we create another table that basically compacts that information every hour or so, and then that batch, we can read the batch off of that for our AI and for our reporting. Okay, so that's more or less the context here. All right, so what happens though if late data arrives, right? This typically means that they're going to actually have to go ahead and run batch processing, but also delay everything. Okay, and that's where things becomes really problematic for us. So in other words, you've got the table that's coming here on the bottom left. Then in the middle, we're compacting every hour, but then maybe because there's issues upstream, this table that's in the middle here, middle bottom here, is going to go ahead and actually have to be delayed in order for us to process that data. Okay. All right. So how do we go ahead and resolve this particular problem? Because there's going to be business requirements where I have to be able to look at the data coming in, irrelevant of the fact that that there's delayed data, because there's still all the other data. So to solve that problem, typically I build a Lambda architecture. So this is what the top stream is. So I still have the bottom stream that gives me my batch data, but then I build the top stream that's structured stream against Kafka, and that is processing data on a regular basis. And then basically build a unified view that validates the data between the streaming data and the batch data. Okay. But of course, it increases the operational burden because you actually have to go ahead and now maintain both a batch process and a streaming process. Okay. And even if I wasn't so concerned about that operational aspect, right, I actually need to validate right? So as the stream is being processed on the top and the stream is being processed on the left, I'll need to write some code and run some code that'll actually validate the data that what I'm reading on the top and what I'm reading on the left, in fact, are the same values. If they're not the same values, then there's excuse me, there's a problem in processing somewhere in between all this. Okay, that's pretty bad. Okay, so I'm going to go ahead and do that. And then if there are mistakes, that means I might have to blow up the partitions and atomically republish all the data all over again. Okay, so it's, as you can tell, this is starting to get more and more complicated, right? But this is traditionally what we had to do when we were looking at trying to do AI reporting, but we actually needed to go ahead and look at both the streaming data and making sense of that data and also the batch data at the same time. And then if I need to do updates and merge, this gets really complex when you're dealing with the data lake in general. So this is just a high level summary of the context here. I don't want to dive too deep into it more, just because the context is, this is the pain, okay, that you are typically working with. And the usual question that we want to ask here is, can this be simplified? All right, so this is where we see if we can simplify it to this point, where basically all it is you've got your streaming and your batch sources to the left. You use Apache Spark to process it into some store, and then from that store, go ahead and do your AI reporting, okay? So what's missing in order to be able to pull this off is the ability to read consistent data while data is being written. And the context is that, don't forget, when you're dealing with distributed systems, it's typically base versus ACID transactions. And base stands for basically available, soft state, but the most important aspect is the E, which is eventually consistent. And what that really means is that when you write the data to your storage or to your disk, typically underneath the covers, whether it's using Hadoop or you're using cloud storage, there's 3 copies of the data, or more for that matter, that are written to disk. Well, that's great because it ensures availability, but the problem is that you're not sure if all 3 are written at the same time. I mean, a sizable chunk of the time it is, but if you want guarantees, no, there are no guarantees for that, right? That's what E stands for, eventually consistent. So it's possible for client 1 to read node 1 and client 2 to read node 2, where client 1 has that file or that data and client 2 does not yet, right? So that means you're inconsistent, right? So if you want that ability to be able to read streaming data and be able to read batch data and simplify your pipeline, you're going to have consistent data. That's the key call out. All right. You want the ability to read incrementally from a large table with good throughput, right? This is the context of us saying, okay, if you actually have to worry about all these small data files, how do I go ahead and handle that? You want the ability to roll back in case of bad writes. That can be extremely problematic. You want to be able to replay historical data along new data that arrives. So in other words, take all the history data, the batch data, if you want to think of it this way, and the streaming data and be able to merge it together or join it together or union it together, right? You want to be able to go ahead and look at the data irrelevant of latency. You just want to be able to treat it as one, so I can, i.e. that unified view, so I can go ahead and actually make sense of it right from the get-go. All right, and just as important, the ability to handle late arriving data without having to delay downstream processing. So in other words, yes, the data comes in, yes, it's late because the source system was late, but that's okay. You know, we're not going to need to delay the downstream processing for it, okay? So the answer basically is this combination of taking structured streaming plus Delta Lake. Structured streaming takes care of that latency aspect for you, but then Delta Lake takes care of the aspect of ACID transactions, schema enforcement and evolution, time travel, rollbacks, all these features put together in order to give you this concept of Delta architecture. All right. And so this idea is that we combine these 2 concepts together. So structured streaming by itself is extremely powerful, but you needed a storage layer that actually provides you those ACID transactions that we refer to. Well, that's what Delta Lake does. And then together, that's your Delta architecture, okay? And so the most important aspects of this, in that case, is that The first one is unify batch and streaming with a continuous data flow model. So in other words, whether you're processing the data, reading the data in streams or in batch, writing in streams or in batch, you're able to do it nevertheless. Okay, that's a super important aspect of that. Okay, excuse me, sorry about that. The second aspect is infinite retention to replay, reprocess historical events as needed. So in other words, you're able to go ahead and hold on to all of the data and then go ahead and replay it. So in other words, if business practices change, business logic changes, or there's a problem upstream that due to the business logic that was applied, you're able to go back and grab all of the data, reprocess it all over again, and actually give you the correct values, right? That ability to clean up the mess in essence. And independently, elastic compute and storage to scale while balancing costs. And in other words, the context is that sometimes it's the storage that needs to scale because you're going to have to hold a lot of data, whether it's permanent or temporary. That's besides the point, but the context is that you might need to scale that. Or independently scale your compute, right? But you don't actually have a reliance where you need high level amounts of compute, but you don't really need large amounts of storage. And because of that, you're forced to increase storage at the same time with traditional systems. Instead, with the ability to actually say, no, I need more storage, then scale that. I need more compute, scale that, but those are independent processes, okay? So underneath the covers I had talked about, okay, well then, in order for us to do this, we need ACID transactions, we need scheme enforcement, we need time travel, and so we've talked about Delta Lake. So how does it work? Okay, so before I explain this concept, let me just switch real quick to a demo, okay? All right, so I've already created a delta table. This basically is called loan by state delta. Up here, I actually already created the table, loan by state delta. And then, but if I look at the file system, here it is, loan by state delta, okay? And so I'm gonna go ahead and take a look at the data. So in fact, what I'll do is take a look at the data inside here. All right, and you'll notice a bunch of small little Parquet files. In other words, very much what you would expect for your Parquet table, okay? Well, what I also have here is a Delta log folder, okay? Oh, let's think here. I might need to clear and rerun this. Let's see. Okay, let me go ahead and clear and rerun this. This is what happens when you run demos live. Haha. All right, so we'll kick this off. All right. And so while I kick this off, the quick call out that I wanted to make was that there is it looks very much like your standard Delta, Parquet table, except that there's also an _delta_log folder. Okay, so I'm gonna go ahead and talk about that real quick when I click this back off. And so what happens here is that the delta_log here is actually your transactions, okay, a log, all right? So let me do that. And so whether you have partition directories, in my example, I don't have partitions, but you could theoretically, you definitely, just like any other Parquet table, you have for your partition directories. Inside there's a file1, file2, .parquet, right? So that's actually what exists. But what's also exists in order to make this a Delta table is _delta_log with different .json files inside there, okay? And these basically tell you the different versions of the table. So as you add more and more of these things, more data into the system, more transactions to the system, there are more transactions, i.e. JSON files, .json files that show up to represent each transaction. There is a question from the audience that, do you get these notebooks as well? Yes, you do. In fact, at the bottom of this particular presentation, there already is a link, but we're also going to email that out anyways. And post it onto YouTube and everywhere else, okay? All right, so let me go ahead and see how we're doing here. All right, let's go back and take a look. All right. There we go. Okay, perfect. So there's only, because I just created this table, because I reran everything all over again, basically we only have a single JSON file. Okay, that's a single file that tells me that I've created the table, okay? So now I'm gonna go ahead and run a stream, all right? So underneath the covers, I'm gonna go back to how Delta Lake works, but I'm just gonna go ahead and show a sort of quick demo of what I mean by this concept of unifying streaming and batch, okay? And so I'm gonna run this quick example on a very small table that basically shows me the loans and the count loans by state, the number of loans you have in each particular state, okay? And so right now, what you'll notice, okay, I'm just gonna run this real quick, and is that I've got a read stream, i.e. it's streaming to read the data from this loan by read stream table. This loan by read stream table is actually pointing to this Delta Lake Silver path, which I've defined early on, which is basically a location. The reason I'm calling out this path is because it's the same path as our batch table. So whether I'm doing this via streaming or via batch, it's actually going to the same file location, okay? And so, all right, so right now, notice that Iowa's null and Washington State's 336, okay? So I'm gonna go ahead and run this now. So for example, when I run this is gonna fail, all right? And why is it gonna fail? Okay, well, let's find out. So let's kick it off. Oh, actually, it doesn't fail because I actually already fixed the code. My bad. Again, running live streams. So, all right, well, right now it works perfectly fine. I had actually left this originally where I forgot to convert this into an integer to a long. And so because it did, it actually would break down. This is the concept of schema enforcement, where basically the Delta Lake will prevent incorrect schema data from being inserted. Now, of course, I went ahead and fixed it already. So now data is going in. So right now I've got this stream of data going in. This is the process rate. It's relatively slow, but the context is that now Washington State, which Iowa, which was originally null, now has 540. Washington, which was originally 336, now is 876. And that's pretty cool. So I'm actually able to read the stream and write the stream at the exact same time. What's also cool is that I can actually go ahead and write yet another stream into this data. So this is my second stream. So I've got two streams writing to the exact same location while I'm also reading a stream from it at the exact same time. And so you notice that Iowa and Washington are jumping up, right? So this is pretty cool because if you look at a regular parquet table or something of that nature, being able to go ahead and read and write from the same table at the same time is actually pretty tricky, if not breaks down. And for that matter, now I'm going to run a batch query against that data. Okay, so select, now you notice it says by loan by state delta, as opposed to the loan by state read stream, mainly because I'm actually reading the batch data, not actually the stream data anymore. And so it's steadily increasing over time. And so originally my batch was at 2070 for Iowa. I go back up, it's actually already at 2880, okay? So because the stream is running faster, so if I run yet another batch inside here, I probably will catch up to that. So let's see what happens here. Okay, it's already at 3510. All right. So I'm going to stop the stream right now. But the context basically is that I can write my streams, read stream, do two write streams and a batch, all the same data, all in the same location, this Delta Lake Silver path, all concurrently. All right. And we can do this under the cover because if you look at the Delta log right here, all right, you'll notice that actually underneath the covers here, I have all these different JSON files for this. So this is a transaction for each and every one of these things to basically go showcase the fact that, okay, I have a transaction. Every insertion by every write stream has a transaction that protects the data. All right, I'm going to talk about this checkpoint in a second, but the context here is that the two streams that we're doing the writes are actually going ahead and now showing up as transactions inside here. In fact, if I was to go ahead and go back and run that describe history, all right, I'm just gonna grab that. Well, actually, you know what? I'm gonna jump to that a little bit later. I'm just gonna look at the files for now. So let me go do that. If you look at, for example, two different files like 14 and 15, 14, 13, you'll notice that basically the timestamp is in here. And then who's the user ID? I was the one who did it, what the operation was. And so, and then what was inside that transaction. Okay, and all the values that were modified as part of that transaction. Okay, so I was doing these changes to Washington State, and I was doing these changes to Iowa State. Right, same idea with a previous one, 13. Right, it's a different timestamp. Okay, it's at 659 here versus 900 in terms of back to the epochs. but same idea. What happens to Washington State, what happens to Iowa State, they're all inside here, okay? Now, this context is important because that's what we're trying to do. We're trying to implement atomicity, okay? So changes to the table are stored as ordered atomic units called commits, right? You commit a transaction. Well, so exactly as you saw in the JSON files when we're running this demo, right? You add a parquet, first client tries to add a parquet, second client tries to add a parquet, or they try to remove a parquet files. Doesn't matter. We record all those transactions, everything that occurs, the changes to the data, the changes to the files, they show up in this .json that you just saw, right? So that way now we have a log that records everything that's happening. And because of that, we can allow multiple streams to be writing to the same table concurrently. That's why you could go ahead and have in Delta Lake, I could go ahead and actually have those two streams writing to the same location and the batch query reading from the same location and the read stream reading from the same location without any problems. All right. But how if there are conflicts? Okay, so if you remember the notebook, I know it's the timestamp, right? So it's really basically, we have a timestamp that tracks everything, okay? So we record that start version, we record the reads and writes, we attempt to commit. If someone else wins, check if you have anything to read, anything you're trying to do has changed and try again. Okay, so in other words, if it's just like adding data like what we did, it's relatively straightforward because, right, even if for sake of argument, two of those transactions were to run at exactly the same time, and they landed it on the exact epoch, what would happen is basically, let's go right to the disk. First client wins, okay, it's written. Second client, it goes ahead and realizes that there's a problem. Now, we could error out, but because we're trying to resolve this optimistically, what we're doing is we're actually going ahead and running it to, we'll retry because we're saying, hey, read the data. What I'm about to do, this insertion, this append, isn't going to actually make any impact, right? Versus an update or delete, right? Which it could have an impact. So in that case, go ahead and just write optimistically, go ahead and write this, and i.e. try again, okay? If it can't do it, by the way, it will error out. So in other words, if you, for sake of argument, somebody's trying to do a delete and update at the exact same time, then what ends up happening is that, sure, one of them will win. The second one that's trying to, let's just say, do the delete will, do the update when the first one was doing a delete. The second one will then fail and roll back to the client and let them know, hey, you just tried to run an update on a non-existent file now, or non-existent set of data. All right. So how do we also process all this data? Because what this implies is that we're adding more and more data right to the system. You add all these parquet files, right? And so these large, just like we were saying, the large tables have millions of files in them. So how do we scale the metadata? So we actually use Spark to scale this. So what actually happens is, like, so each of these JSONs comes in, we add parquet, remove, whatever it is, they have these transactions. And after every 10 of them, we'll do a checkpoint into parquet. And so then that way, when we need to read the table, we're going to first read the transaction log, but instead of trying to read every single JSON that's inside there, we're going to read the parquet files of our transaction log, the checkpoints, put that into memory. So that way it only actually has to read the new JSON files. Okay, so the new transactions. And then we can easily keep track of all the files that have been changed in the system. So let's go back to the demo real quick. You'll notice if I scroll back up, on the 10th one, it says checkpoint parquet, right? And then on the 20th one, same idea, the checkpoint parquet. That's exactly what's happening here, right? This goes back to that scaling metadata, right? We've checkpointed it so that way when we're trying to read the transaction log, we're only reading the new JSONs. The checkpoint parquet basically lets us store it statefully, but then also chuck it in memory such that when it's time for us to do scans or know what transactions we're on, it's already in memory. If you shut down the cluster or bring up a new cluster and you need to scan and understand what's going on again, it'll just simply go ahead and read all the parquets right away. So put that in memory, and so it'll only have to read 21st and the 22nd files to figure out what's going on, okay? All right. So that's actually how Delta Lake works under the covers. All right. And so the Delta architecture, right? Let's go into that specifically. So how do you connect all these dots together? So as we just shown, we have the ability with the Delta Lake to go ahead and put ACID transactions. We have a transaction log. We can even enforce schema, though I didn't do the demo well, so my apologies for that. But how do I put this together to simplify my flow, right? How do I connect these dots together? So the ability to read consistent data while it's being written. Remember that quick demo I wrote had one read stream, 2 write streams, and 1 read batch, right? Well, because there's a snapshot oscillation between writers and readers, I'm actually able to do that now, right? I can, that's the demo you saw. You are able to see us going ahead and doing reads and writes, whether it was stream or batch, it didn't matter. All right. You're able to read incrementally from a large table with good throughput, okay? So how do I do that? Because we had optimized file source with scalable metadata handling. And that when you saw the JSON and the checkpoint parquet, that's exactly the point, right? That those checkpoints allow us to basically ensure that the metadata can scale as well. It's bad. It wouldn't be good if we could scale the data itself, but did a horrible job with the metadata, right? So that's why we do the checkpoints to make sure it's easier for us to scan the metadata as well. So that way it knows exactly what files it's supposed to read. We also have the ability to roll back in case of bad writes, in this case, time travel. So what's time travel? Well, let's go back to demos for that. All right, so, excuse me. I'm just going to skip past. We actually have this notebook, by the way, which we will share, actually has a lot of cool other examples, but I just wanted to show you the main things here right now. So let's go back and look at this table. All right, so before you can look at the JSON files, but I'm just going to run it in terms of, so you can see it this way, okay? So remember how the JSON files, there are 22 of them. Well, this is just the history table that shows you the initial creation, 0, okay? And then also all the 22 different versions of that table as we loaded the data up, okay? All right, so what's great about time travel basically is this. So if I wanna go back and look at what the, look at the loan by state delta table as of the 0th version, all I have to do is specify version as of 0, and what you have here now is Iowa back to a null value, okay? So Iowa's null and Washington's 336. That was the version of the table when it was originally created, right from the get-go. All right. And then we remember how what we did is we added 2 write streams to load up the data. So I'm just going to choose number 9. Okay. And so this is the 9th version of the 22 different versions we have. Okay. For this particular example. And by the 9th version, Iowa was at 1215, Washington is 1821, and California is still at 2006 as of version 9. As of version 0, right? Because there was no difference. In fact, every other state didn't change. It was only Iowa and Washington State. And then, but don't worry, if we want to get the original data back, you can either specify the version as the current version, or don't even bother specifying the version at all. And here's the current version, where Iowa's now at 3915 and Washington is at 4971. All right. So this concept of time travel basically allows us to go ahead and go back in time and find out exactly which version we want to go to and make changes as you deem fit. It could be something as cool as just showing an animation like this, where you're simply seeing what the different version looks like. In a previous session, getting data ready for data science with Delta Lake and MLflow, I showed a version of this notebook that allowed us to identify model drift or data drift, where as data changes over time, that we could go ahead and we could actually monitor that and see the impact of that on our machine learning model. The same comes into play, right? It could be something as simple as that, or something as complex as running rollbacks, which is you realize, hey, the last 10 editions or updates to this were actually incorrect. Let's roll back to a previous version. Let's roll back for sake of argument to version 9. So no problem at all. We can go back and do that, right? Because the data still is there. All right. So let's continue back to slides. All right. So The fourth, back connecting the dots again, the ability to replay historical data along new data that arrived, right? Well, then stream the backfilled historical data through the same pipeline. So in other words, if you've got a source that contains all the old data that was delayed, not a big deal. Just go ahead and stream it through this exact same pipeline. Or if you've got another source, or you need to replay it all over again because the business logic has changed, again, you've got the full source. It's basically stream right back to the left and have that run this exact same process all over again. And the ability to handle late arriving data without having to delay downstream processing. And in this case, straightforward, stream any late arriving data added to the table as they get added, right? Because now you simplified it. So the context here is now the Delta architecture with Delta Lake allows you to continuously create a continuous data flow to unify your batch and streaming. Like again, the demo was relatively simplistic. Typically, it looks something closer to this, where you have multiple sources resulting in multiple tables or multiple data stores even, right? And this concept of that we have, you see here's bronze, silver, gold tables in between. It's all because you're trying to merge different tables, different data sources together with different levels of data quality, right? So it seems like it's more complicated by doing this, but the whole premise is saying that I can now actually have a single pipeline, back to this thing, right, to do all of these things, all right? And so that's how we connect the dots together. So now that I've talked about this, let's talk a little bit about the characteristics of a data architecture, okay? Excuse me. Oh, actually, I'm gonna jump real quick into a question because there's some good questions before I talk about Delta architecture. Let me actually answer some questions here, okay? What causes a version update? Is it related to checkpoint? Let's break those two things down because they're actually different things. The checkpoint itself is every 10th version or every 10th transaction to that table, we're going to do a checkpoint. So that way it creates a Parquet file. That Parquet file then gets loaded into memory, right? So this way, instead of actually trying to read all these small JSON files, because, you know, just like any other Spark infrastructure or any infrastructure, right? The more small files you have to read, the larger the overhead to do it, right? So instead of actually doing that to you, what we do is we create these little Parquet files and we put them into memory. So if it's an existing process, existing cluster, Spark cluster that's running, no problem. It's already floating in memory. And then only the new JSON, the new transactions actually have to be recorded, right? And processed. And then by the 10th one, again, we checkpoint it and we chuck it back to memory. If you shut down the cluster and you start a new cluster to access that table, the Parquet files are there. So instead of actually reading all the JSON files, it'll just read all the Parquet files. And so it can actually chuck that stuff into memory faster. So it knows exactly what transactions that actually happened, okay? So what causes a version update? Well, the version update is actually a transaction. So in other words, any changes that you do to the table. So an insert or an update or delete or merge, that's actually how you would physically go do this, okay? So hopefully that answers that question, right? Now, related to that, there's another really good question, okay? Is it possible to update a, excuse me, how do I delete a version of data, okay? So typically, if you want to delete something, you're deleting the data itself as opposed to deleting a specific version of it, okay? Now, there's this concept, the reason why is because from a GDPR compliance perspective, you want to be able to record every single transaction that occurs, okay? That's actually the context. So what happens is that if I want to go ahead and remove all of those files though, right? Because what's implied very strongly here is that when you run a delete, you actually don't delete it, right? You've kept the files. That's why I'm actually able to see the 0th version and the 9th version of the table, because I actually still have the old files. I just simply have a transaction log that tells me which version I'm supposed to be looking at or which set of files I should be looking at when I request for an older version of that data. But if I don't go ahead and actually, if I do really want to remove it, well, how do I do that? That's running a vacuum, okay? So by running a vacuum statement, basically you clear out the files. By default, any files that are 7 days older, Okay, so in other words, what happens that when I run the vacuum, it clears out the data. Once it's cleared out, then if I go back and request for that old version of the data, it'll give you an error message simply saying that data no longer exists. But you still have a transaction log that denotes all the actions you did to the table up to that point. But yes, the data no longer exists. Okay, if you need that data to be removed right away, then instead of using the default 7 days, just specify, for example, 0, right? So that'll just mean get rid of everything right from the get-go. Okay. All right, perfect. So let me go ahead and talk about the Delta architecture a little bit more, the actual purpose of this session, okay? Here are some of the key tenets that we really want to do for this, okay? So you basically want to adopt a continuous data flow model, okay? And what we mean by that, by the way, is that you want to stream to and from the Delta Lake table whenever possible, okay? So in other words, it's not just about going ahead, even if you think of the problem as a batch problem, you actually, if you can just think about it purely from a standpoint of like, all the jobs are stream jobs and all the jobs are to and from the Delta Lake, it allows you to go ahead and do these 3 tenets. You can unify back to stream, same engine, same API, same user code. There's no need to reason about system complexity separately, okay? And then you're able to incrementally load the new data very efficiently. Okay, in other words, there isn't a need to do state management, okay, on what new files are added. Okay, you basically incrementally add and you're good to go. And then you process the data super quickly, right? So there are limited delays, minimal delays to no delays. Okay, so I forgot if I included this in the slide, but one cool example that we had from last year's Spark Summit in San Francisco, where one of the keynote speakers was Comcast. And what's really cool about the Comcast scenario is that they used to have 84 jobs, okay? And this is for this particular example of their system. The sessionization is basically with the 84 jobs, because they're able to use Delta Lake and because they had to ACID transactions and because they follow the Delta architecture, they converted those 84 batch jobs into 3 streaming jobs, right? So from a maintenance and operational perspective, you've simplified the workload massively, okay? All right, so let's see, use intermediate hops, okay? Materialize the data frames whenever it's applicable, especially when a large number of transformations involve, right? Your materialization can be used for fault recovery, easy troubleshooting, and multiple consumers are expected, all right? So what I mean by this is this, right? Traditionally, right, if you've got a source table and you get your destination tables, what we'll do is we'll do multiple transformations, okay? And so these intermediate data frames that you create are typically sitting in memory, okay? And obviously you do this because it's faster to process this data in memory, okay? What we're saying is that if you actually have concerns or have questions or want to be able to ensure that if there's a breakdown in task because the transformation you have is relatively complicated, well, what I ask you to do is like, well, why don't you create an intermediate table, right? It actually simplifies some of the flow. For example, in this example, tables 1, 2, and 3 were actually useful for both the output destination tables. It was just from table 3 onwards, we needed actually to go ahead and to do something slightly different. So instead of creating 2 separate set of tables with the exact same data, go ahead and actually run an intermediate table, save that to disk, and then run 2 separate processes for table 4, table 6, table 5, table 7 are on a different stream, and they go to different tables, right? It really simplifies the flow here. And by the way, I apologize, but for some reason, my Q&A panel is not showing up. So in fact, I want to ask you if it's okay for you to post your question to the Zoom webinar chat. I realize that's actually not a good best practice, but for some reason, my Q&A panel is not showing up right now. So please put them in the Zoom webinar chat, okay? And sometimes because you have an issue where you don't know if the data is partitioned correctly or you're running into skews or whatever else, yeah, you put the intermediate table even earlier up, and that's perfectly fine, okay? So the context, again, from a standpoint of fault recovery, multiple consumers are expected, easy troubleshooting, boom, go ahead and actually use the intermediate hops, okay? All right, and so now that we've said all this, what's the cost versus latency trade-off? Okay, so for example, if you've got streams of data arriving continuously, what's implied is that you have an always-on cluster, right? And you're continuously processing data to do that. That in itself seems like an more costly potentially, right? So how do you get around that, right? There's examples. For example, you run frequent batches. Data is arriving every few minutes, or even say 30 minutes, whatever. Use a warm pool of machines. So then turn off the cluster when it's idle. Start the cluster when the data needs to be processed, and then you, for example, using the streaming trigger.once mode, so the cluster will just kick off, and you're good to go, right? Or if you've got infrequent batches, you got data arriving every few hours or days, turn off the cluster when it's idle. Start the cluster when the data needs to be processed. Again, use streaming trigger.once mode. Okay. The context basically is then potentially you can go ahead and actually run the clusters or kick off the clusters only when you physically need them. Okay, to make sense of it. Now, one thing to note, for example, is that when Comcast, back to that example, went ahead and switched over, because of the efficiencies for them to run this continuously with 3 jobs instead of 84, they went ahead and shrunk down from 640 VMs to 64, a 10x improvement, i.e. reduction of the number of virtual machines. So the cost of them doing this massively decreased by going ahead and actually keeping the cluster on for continuous processing. So you're going to have to, take everything in stride. All right. Another important aspect of the Delta architecture is also being able to reprocess this data, right? So infinite retention of raw data plus stream that means you've got a relatively trivial recomputation of that data, okay? And oh, by the way, the question was asked, like, what is trigger.once? This is part of structured streaming. So we actually will have a separate session to dive deeper into structured streaming. That'll be coming up in the next few weeks, in fact. So we'll talk about that then. But the context is basically within structured streaming. Once you run the trigger, it basically tells structured streaming, okay, data is in, trigger it to run it, and we can also tell the cluster to go ahead and kick itself up to start processing that data. Okay, and so what we mean by this reprocessing perspective is that you can simply clear out the result table and restart the stream all over again. Okay, so in a previous session, we dove deeper into this concept of bronze, silver, gold tables for data quality. The idea is that the bronze is your raw data dump. You just dump the data and you put it inside there. The silver is this concept of filtered, augmented, and cleansed data. So as you progress from bronze into silver, the data is a lot cleaner. And then from silver to gold, you do the final bit of augmentation or cleansing. So that way you can run your BI or AI or data science or machine learning against that data. These are all really good things. But the context is that how about if the business logic for the augmentation or cleansing was incorrect or needs to be updated? Well, that's what's great about it. You still have the bronze table that has all the raw data from the first place. Go ahead and reprocess that all over again. Okay, and then you can recreate the silver, recreate the gold, and you're good to go. Right? Leverage cloud elasticity. So in other words, because you have to go back in time and reprocess all the data, scale up. Right? Add more nodes, purely for the purpose of getting that backfill figured out. Once that backfill is figured out, boom, flip the switch. You can scale back down and to your regular amounts of processing. Okay. And this, oh, actually, there we go. Tune the data quality, right? So this is what exactly I was just referring to. So I forgot that I'd done this, but basically here in the bottom left, here's your streaming and your batch sources as you're progressing from left to right, from bronze, silver, gold. This allows you to improve that data quality such that whether it's streaming analytics or your AI reporting, you're good to go. In the process of doing this, you want to go ahead and ensure to enforce, but also be able to merge the schemas. Okay, so there are times where you want to enforce the schema. You want to ensure that any data that comes into the system isn't going to go ahead and break or bring corruptible information, corrupt the idea of that table. Okay, typically that's done at more of a silver or the gold level where you enforce the schema, versus where at the bronze level you may want to merge the schema, right? Where you basically want to add new columns as they come in. But what you want to do is you want to make sure that you when you allow the schema to evolve, it doesn't matter really in which level, right? When you do want it to evolve, you want to make sure that it actually is what you want. So by definition, Delta Lake enforces a schema, and then you have to specify that you want to evolve the schema. So that way, you know, you're actually going ahead and making changes to the schema, right? You don't want to do this as a haphazard function, okay? All right, so like I noted before, here's a summary of those key characteristics, right? Adopt a continuous data flow, use intermediate hops to improve reliability and troubleshooting, and make the cost versus latency trade-off based on your use case and business needs, and optimize the storage layout based on your access patterns. Reprocess the historical data as you need and incrementally improve the quality of your data so it's ready for consumption. Okay, these are the key characteristics of what you have with the Delta architecture that will allow you to simplify your flow. Okay, the benefits of this architecture then reduces the end-to-end pipeline SLA. It reduces the pipeline maintenance burden, eliminates like Lambda architecture for mid and latency use cases. It actually handles updates and deletes easily. I didn't get to show it in today's demo, but you can run update and delete statements and merge statements directly against your data using either the Python Scala APIs currently, or once Spark 3.0 comes out with Data Source v2, with Delta Lake, you're going to be able to run that with SQL statements as well. Also be able to do deduplication. And then, you know, lower infrastructure costs with elastic independent compute and storage, right? Like I said, we have organizations reduce the infrastructure cost by up to 10x, and that's exactly what Comcast has done. Again, Spark Summit San Francisco last year's session, the keynote, they talk about that, okay? And so in a nutshell, that's what the Delta architecture is, right? To process data continuously, incrementally as data arrives in a cost-efficient way without you having to choose between batch or streaming. Okay. So one thing I wanted to finish off with before I go dive into the rest of the questions is that, you know, as more and more people are starting to use Delta Lake, in fact, we have, there are more and more connectors. So Delta Lake can talk to Hive, so obviously Spark, Presto, Redshift, Athena, Snowflake, right? And that's the current, as of today, this is rapidly going to change, i.e. adding more to the list, okay? Hive is currently in, I believe there's a question that came up on the chat. Hive is currently in private preview now. We're working with the community to make this available so that way Delta Lake can go ahead and work on Hive for public preview, obviously. Okay. There's a lot of our partners and providers. So whether it's your Tableaus, Informaticas, Click, StreamSense, Talend, Attundi, Windisco, Professora, you know, that actually work closely with us. Recently it was announced by Google Dataproc that they also will be reading Delta Lake themselves as well. So this list is going to rapidly grow as well. And so the ecosystem is growing as more and more people and companies are recognizing the benefits of actually having transaction protections around their distributed storage systems. Okay. And let's see. Okay, and plenty of users Delta Lake. Actually, just go to delta.io to see the full list. So this is just a partial list of it, but there's a lot of companies out there that are already standardizing on Delta Lake in order for them to run. In fact, Databricks itself actually, more than 75%, 2 exabytes of data per month are actually processed using Delta Lake now. So it's a pretty well used, well productionized project at this point. So if you do have any questions, please join us at delta.io. We actually have a pretty active community, whether using GitHub or Slack or whatever else. We're pretty much talking all the time, answering questions. So if in case I'm not answering questions now, you can definitely chime in there. And I did want to leave also, I'd love for you to join us at Spark Summit, Spark and AI Summit 2020 in San Francisco as well this year, from June 22nd to 25th. And so if you want to, please use the discount code Denny SAI 020 for a 20% discount for coming to Spark Summit. Okay. So with that, I'm going to leave about 5 minutes to answer any questions. Please continue putting your questions inside the webinar chat, not in the Q&A. Karen was right to say originally we should have done it there, but due to the fact that there's a problem with the Q&A panel on my screen, at least, I can only see it in the webinar chat. So my apologies. Okay. So a great question. For starters, what are the performance implications for storing historical data forever? Whether you're slowly changing to, or whether you're querying new or historical data. The performance implications for storing the data forever is pretty much the same as what you would expect as when you have too many small files and you have many of them, right? Over time, it gets larger and progressively gets slower. The only way to speed things up is to go ahead and actually put more resources to compute against it. Not really the optimal thing. So then I just talked about time travel, and you said, hey, but I can do time travel and I can go ahead and go back and figure out what's going on, and I can keep historical data if I want to. Yes, you can, but those are, as you can now tell, they're sort of slightly competing with each other. So obviously every practice is a general rule of thumb and can easily be broken, but the general rule of thumb is you keep the data for about 3 months, right? Long enough for you to avoid the oops issues, right? In other words, I accidentally deleted this, or I accidentally updated, or I accidentally inserted this data, right? Long enough for the oops scenarios to be solved, long enough for you to, for sake of argument, take care of looking at model drift or data drift as data changes over time to see how that's impacting your machine learning model without actually having a massive cost to the system on holding all of that data. And then invariably the question will be, hey, how about if I want to keep older versions of the data? Well, then in your case, at least right now, what we would suggest is go ahead and then save that version of the table. Since you can go, for example, select star from loan by states delta, where version as of version 9, right? If you need that version 9 table, what I do is just simply query that table and then create a new data frame, a new table, store that table as a separate source, right? A separate location. So that way you can always refer to that version of the table, put it in archival store. So that way it's not like you're not like frequently going to get it, but for sake of argument, if you wanted to look at what the financial snapshot of the data was as of end of financial month end, right? Then a good way is to say that, okay, I need to keep those snapshots. So let me go ahead and save that data into a separate store that just contains that data and only that data, right? So that way you can still go back in time, get that version of the data, like I said, that financial month end, right? Without actually going ahead and adding to the burden of actually trying to query every single version of data when you realistically only need like maybe 12 versions a year, okay? So hopefully that answers your question on that one. All right. So another really good question is, how can I handle dynamic schemas on Delta tables? Can Delta tables create new columns dynamically depending on the schema? It potentially can, okay? So there is a option called dot option merge schema equals true. And that basically means, it implies what it sounds like, which is when I specify that, that means I'm telling Delta Lake, you can go ahead and merge a schema and say, hey, I've got a column blah that was not in this original table. Let me go merge that together now. Let me add that in, okay? And so that's what merge schema is true. So the key context isn't that you can or cannot do it. Excuse me. The key context basically is that you're able to go ahead and by default enforce the schema to prevent users from accidentally overwriting or accidentally corrupting the table, right? That's by default. We want to prevent that from happening. But then if you know you need to make the change, then by specifying dot option merge schema is true, you're able to go ahead and make that change. And so you use that concept very sparingly as opposed to run that all the time, just because you don't want people to change the schema on your table all the time, okay? So hopefully that answers that question. Okay, I'm going to answer 2 other questions to end today's session, but all right. So there's a question here is like, as a best practice, should I keep versions of data only for small data, or is it a good practice for huge data and to keep those versions as well? And so the good practice actually is not so much the size of the data, it's more your business use case, right? Uh, for financial information, I definitely have seen it common where I will go ahead and save. Like I said, I'll keep the versioning on my Delta Lake table on for 3 months, and then I'll constantly clean it out. But by default, 7 days. And for some people, that's perfectly fine. Okay. And by the way, you actually have to run the vacuum. It's not like it automatically happens. You run the vacuum and it just says, okay, well, anything older than 7 days, go ahead and remove. Okay. But so it's perfectly fine for you to go with that. Often, like I said, it's more like closer to 30 days or 90 days due to for debugging purposes. But then, just like I noted, where for like financial month ends, where I want to keep know exactly what the financial amount was for that table because I'm doing fiduciary responsibilities. I'll save that actually into a separate table for archival purposes only. And then the idea is that if I have any issues, I can go back and look at, okay, well, what we reported in the month of January, because all our financial reports generated for the month of January are based off of this version of the table. And so, same thing for February, March, and so forth and so forth, right? So that's the context. So the best practice concerning archival or keeping all these different versions is really dependent on your actual business use case. Okay, so hopefully that answers that question. And the final question that I want to answer is that there's a question concerning training schedules, training sessions that are scheduled from the 22nd to 25th of June, and those were posted yesterday. Are those training sessions going to be recorded and available later? In general, the training sessions for Spark Summit themselves are not made available for view. They're meant for people who actually attend the conference, because it's actually hands-on sessions where you get to come in, get to work on the sessions. We have TAs and experts in the field that go ahead and not only teach the course, but also answer all the questions. So the context basically is that, yeah, it's hard for us to go ahead and record those, just because the amount of time and effort spent for not just the attendees who are coming to listen and learn, but also from the people who are teaching all the stuff, and you get to ask questions from. So hopefully that answers all your questions for today. I know there's some other ones, but I'm cognizant of the time, and we're just about the top of the hour. So I did want to leave it with, thank you very much for taking the time to attend today's session. We will have another session next week about simplifying scaling data engineering pipelines with Delta Lake. So I'd love to have you join that. Meanwhile, if you do, we'd love to also see you at Spark Summit. So please join us. And here's the discount code again, Denny SAI 020, and where you get 20% off. I think that covers it for me, Karen. Any